Okay, welcome back, everybody. This is question 51 of Chapter 11. It's also Chapter 2 of our little mini-series on intermolecular forces. So now we're going to do a little bit of application considering. All right, so we're going to look at an order of some compounds. Got 4 of them here. We're going to put them in order of increasing boiling point. So the way to think about this is that, like, if it takes a higher temperature to boil, that means that the intermolecular forces in the liquid phase are stronger because they're holding the molecules in there for longer, right? At higher energy. So you could also think of it in terms of activation energy thresholds. Like, for boiling to happen, you have to achieve a higher threshold of energy to move those particles into the vapor phase, right? There are just a few different ways to say the same thing. But the basic idea is we've got these 4 species. Last question we talked about different sorts of intermolecular forces. If we recall, we had dispersion forces, which is uneven electron distribution that creates really temporary transient positive areas and negative areas in the molecule. We had dipoles, which are just polar regions in molecules where there's concentrations of electrons or non-concentrations of electrons. Those can be permanent just in the molecular structure and sort of inherent and characteristic of them. They can also be induced by ions and by other dipole molecules. And then we saw hydrogen bonding as an extreme example of the dipole interactions. Okay, so now let's put these things in order. So let's start with the methane, with CH4 here. So CH4 is non-polar, right? CH4 looks like this. It is the textbook tetrahedral geometry. All hydrogens around it, so I mean, it doesn't really matter if it's hydrogens or chlorines, as we saw in the last one. But point is, if there like other methane molecules around it aren't going to be, like, the hydrogens are not going to draw the molecules together or anything like that. And because there's hydrogens in the way, then the carbons aren't interacting particularly strongly with hydrogens of adjacent molecules. You're not going to see lots of that happening either. So all those mean that like there's no polar regions, means there's no dipoles, and there's not going to be any hydrogen bonding either. So we got dispersion forces only, and because this is just carbon and 4 hydrogens, we don't have very many electrons in play. That means we have weak dispersion forces at that. That means that this is going to have a very low boiling point. Right, so low boiling point because of the weak dispersion forces. Okay, so let's we're supposed to be putting these things in order. So let's just assign this. Let's give these things a 1 to 10, where 10 is like super strong and 1 is really weak. Right, so let's give this. We're not gonna have weaker than that, so let's give that a 1. Okay, next we have ethane. So ethane is very similar to methane. As I'm sure all of you know. So while I'm drawing this thing out, then what could possibly be different in this case? Like, so we're again not going to see hydrogen bonding. We're not going to see dipoles, right? Once again, we've got hydrogens arranged about in like a tetrahedral format, even though we've got carbon to carbon bit here. Like, these are evenly distributed over the molecule, so there aren't any polar regions, right? So no polar regions, no dipoles. Okay, so we're not worried about dipoles. We're not worried about hydrogen bonding. So we're looking at just dispersion forces again. So what's going to have more dispersion forces then? Are we going to see more in ethane, or are we going to see more in methane? And the answer is we're going to see more in ethane. And we're going to see more in ethane because there are more electrons in ethane. When you're just looking at dispersion forces, your ability for intermolecular, like, interaction, in a sense, becomes a function of how large your molecule is, meaning how many electrons it has in it at play, right? So because ethane has more than methane, these are going to have stronger dispersion forces just because of the larger amount of electrons. So again, we're not giving this thing a very big number, but it's got to be bigger than methane. So let's give it a 2. And we'll just cross our fingers we don't get into trouble later. Okay, so far 2 dispersion forces. This is pretty easy. let's have a look at our next one. Now we've got 1-chloroethane, or chloroethane for you guys going into organic next year. Let's quick sketch this out. We've added a chlorine. Otherwise, this is just ethane. Last time, oops, that's not wrong. Well, that is wrong. Sorry, but that's wrong in a way that that you might not know yet until you see organic next year. These have to be oriented different directions. So if you're staring at this from the back, right? These are the ones out in front, right? You can see they're blocked by this molecule. It means that these ones need to sit like this, right? And this is the way you have the least amount of interaction between those. But like I said, that's out of the picture now. That's just stuff I should be remembering now. Okay, and we've got a chlorine added to the end of this. So obviously this is going to be our species of interest. This is very electronegative, right? And it's not surrounded by hydrogens anywhere near. So that means that this is going to be a very delta negative region, and that's going to make the rest of this a delta positive region. So we've got dipoles finally, right? If you picture more chloroethane over here, because this is going to be very much attracted to the hydrogens surrounding these, right? You're going to have a lot of dipole interactions, and they're going to be pretty strong. All right, so we got to give this one a pretty serious number. So let's give this a 6. All right, 6 for the dipole. Oops, I erased some of our ethanol there, but we know what we're after anyway. Okay, last one, ethanol. Ethanol. So, I guess if I was really smart, I could have left most of this there, and I wouldn't have had to keep redrawing this. But all right, same mistake as last time. Don't do that next year. Or something like that. You get the idea. And our OH group, right? You know that we've got tons of lone pairs at play here. You know that oxygen is one of the species that is able to hydrogen bond. So in ethanol, we are going to see hydrogen bond interactions, right? Hydrogen bond interactions win between all of the intermolecular forces. No matter what else you're looking at, the interaction between the oxygen and the hydrogen on the next one up is just way too strong. So that is going to be our ordering. We're gonna have we've written them in order actually in the question. We're gonna have methane less than ethane, less than chloroethane, less than ethanol. And remember that we were talking about these in terms of boiling points, right? So think of this in terms of in terms of energy here, and this being the reaction process. For if you have a larger boiling point, it means you're going to have a massive energy activation threshold here to get yourself from the liquid state into the gaseous state. Right, that's what this chart's showing here. Don't think that this is a phase diagram either. That's not true. Yeah, don't you dare think that's that. Okay, and then if we have one with a lower boiling point, that means we have a lower energy threshold to get over. Same sort of idea here. Okay, hopefully that's helpful. We'll see you in the next question for chapter 3 on intermolecular forces.